Welcome back to the Chem OG. Today we're going to talk about carbonyls, and carbonyls are rather biologically important. And carbonyl compounds, and what they are, is that they're a compound that contains a carbon-oxygen double bond. That's all they need to have. And under that umbrella come a whole host of functional groups. So we can take a look at things like ketones, acid anhydrides, aldehydes, amides, esters, carboxylic acids, lactones, lactams. So there's a whole bunch of functional groups that are carbonyls. And what we're going to talk about today is sort of characteristics that are relevant to all of these carbonyl compounds. And so when we take a look at a generic carbonyl compound, we have an oxygen and a carbon in a double bond with each other. And that has some pretty big consequences in terms of the chemistry of this molecule. And so within that carbon-oxygen double bond, the oxygen has a partial negative charge and the carbon has a partial positive charge. And that's a result of the fact that oxygen is more electronegative than carbon is. And so the carbonyl carbon, so the carbon itself, this one right here, the one that's immediately double bonded to the oxygen, that carbon is electron deficient. And because it's electron deficient, and because it would like to get back to neutrality, it would love some electrons. And so we have a term for atoms that love electrons. We call them electrophiles. Okay? And that is equivalent to a Lewis acid. So electrophiles, Lewis acids, those are interchangeable terms, and they mean the same thing. All right, so we've established that anytime we have a carbonyl, regardless of which of the functional groups that I quickly ran through or others that are out there that are also carbonyls, all of those compounds, they have this characteristic in common, is that the carbonyl carbon can react as an electrophile. Now, the carbon adjacent to the carbonyl carbon is given a very special term, and those are called alpha carbons. So if I take a look at this molecule right here, the alpha carbons are the ones that are immediately adjacent to the carbonyl carbon. So this one is immediately bonded to the carbonyl carbon. This carbon is bonded to the carbonyl carbon immediately, so that's an alpha carbon. And if I branch out one more carbon from there, those are known as beta carbons. Okay? And the reason we give those carbons special designation is because of the existence of that carbonyl functional group, that's going to have some bearings on the chemistry of this molecule. So let's take a look. So here's that same molecule again. And what I'm going to do is I'm going to put in the hydrogens explicitly. So I'm going to take that, replace that structure and put in the hydrogens explicitly. Now, we mentioned that the carbons attached to the carbonyl carbon are known as alpha carbons, and the hydrogens attached to those alpha carbons are known as alpha hydrogens. Okay, so the hydrogens attached to alpha carbons are known as alpha hydrogens. And the hydrogens that are attached to alpha carbons have very special chemistry. But before we go into them, let's talk about hydrogens in general. So when you have a neutral hydrogen atom, it's got a single electron on it. When you have a hydrogen with an extra electron, that's called a hydride, and it has 2 electrons. When you have an H plus, though, that has 0 electrons. Okay, so if we remove an H plus from a molecule, we're removing something that has 0 electrons associated with it. So when I take a look at that same molecule with the hydrogens explicitly intact, let's talk about some chemistry associated with that. If I pluck off one of those alpha hydrogens, right, and in particular, if I pluck off an H plus, that H plus is acidic. Now, normally a carbon-hydrogen bond is not acidic, but this particular hydrogen is, and that's because the conjugate base that I form is stabilized by resonance. So if I get a base in here and that base takes away an H plus, remember this H is going away with 0 electrons. So that means that both of the electrons in this bond are going to have to go to carbon. So a base is going to come in, it's going to take an H away, but those electrons in this bond right here, they're going to go back to the carbon. And so what I form is something that is not so stable. It's a carbanion. Now that carbanion, though, has the benefit of resonance. So one of the modules that we covered earlier, talked about the possibility of resonance when you have a charge right next to a pi bond. And so the negative charge on that carbon, or that newly formed lone pair on that carbon, can go through resonance with the carbon atom that's next door, and that'll kick up the pi electrons that are here up to the oxygen. And so what I end up with is an alternate resonance form in which I now have a new pi bond between these two carbons, and this pi bond is gone, and now I have a negative charge on the oxygen. So between these two resonance forms, the one with the oxygen with a negative charge, as opposed to the one with the carbon with a negative charge, the one with an oxygen with a negative charge is more stable, and the one with the carbon with a negative charge is the one that's more reactive. Okay. So if I do take that stable form, if I do take that stable form and protonate it back, so put a proton back on this molecule, what I'll end up with is a structure that looks like this. And that structure is known as an enol. And the way that you can spot an enol functional group is that you have an alkene functional group, a carbon-carbon double bond, and you have an alcohol. So you got both of those things on the same carbon. So both the alkene and the alcohol are attached to the same carbon, and that's what makes an enol functional group. So if I take this enol functional group and I deprotonate it back, well, I'm going to call it an enolate. Okay, so that ate suffix is very characteristic of molecules that have a negative charge. So examples like bicarbonate, sulfate. Here we form an enolate by forming the conjugate base of the enol. Now, remember we said that this enolate right here is the more stable form of a structure. Okay, so there's a reactive form of the carbanion, and there's the more stable form with the oxygen with the negative charge. But remember, when you have resonance forms going back and forth like this, those aren't different molecules. Those are actually the same molecule. So that means when we take a look at enolates, enolates are reactive at the alpha carbon, right? They wouldn't be reactive at with the more stable version. They'd be reactive with, the more reactive version. And so the reactivity is actually happening here and not here. And that's something that's very worthy of noting, is that when you have a molecule with a negative charge on the oxygen, that's the more stable form, yes, but the reactive form is with the carbon. So that carbon is nucleophilic. And so carbonyls are electrophilic at the carbonyl carbon. We've already established that from the beginning. And as we just learned, they're nucleophilic at the alpha carbon, but in order to get them to be nucleophiles, what we had to do was we had to remove an alpha hydrogen. So with carbonyls, we have something that's very interesting. It's both a nucleophile and an electrophile, and that means that these molecules can actually react with one another. So today was a brief introduction to carbonyls. We'll explore the rich chemistry of carbonyls a lot more in the upcoming modules. Thank you very much for attending today's lesson. So don't forget to subscribe and don't forget to hit the like button. If you have any feedback, please leave it in the comments section and look forward to seeing you at the next lesson.